Everybody. I hope you're doing well out there. It is April 29th right now when I'm filming this. It's a beautiful spring day outside, so I hope you're enjoying that. I know you're staying on top of your schoolwork. Thank you so much for all the hard work. Keep it up. We are going to today talk about properties of atoms and elements and subatomic particles. This will be essential for where we're going still in our star unit. But before I jump into that, got one piece of housekeeping, an announcement that I want to share with you all, that we have been asked, all your teachers have been asked, to make sure we're doing at least one mandatory Google Hangout a week. So our mandatory Google Hangout will be every Monday, starting next Monday, May 5th. It's going to be just quick 15 minutes from 10:45 to 11 a.m. It'll be a time for us to connect, say hello, do an attendance question, do attendance, give an overview of the week, and then if you have any questions for me, you can certainly ask them too. I am going to do only one of those on Monday morning every week. I will keep the Wednesday optional Google Hangout open just as it's been for those of you who want to pop in, ask questions, get feedback as you need it. So please let me know if you have any questions about that. We're using the same Google Hangout link, which is linked all over the place, including in the need to knows and the weekly modules. And I will send it in an email right after I shoot this video. All right, so today what we're going to do, hopefully, is learn how to calculate properties of atoms and subatomic particles for a given element. And you might think that that's way outside of what we've been doing. We've been talking about stars, these really huge objects off in the night sky. Why are we zooming in on atoms now? And that's because one of the most important things that stars do is create new elements. The Big Bang primarily created just hydrogen and a little bit of helium. So where do all the other elements in the universe come from? Well, they are cooked up inside stars, which are like big element factories. So I'm going to jump right into it here. Elements are the purest form of matter. That means they cannot be broken down into simpler substances. And atoms are the microscopic and indivisible building blocks that make up the elements of the universe. So elements are made up of atoms. I just said that. Atoms make up elements. And all elements are arranged systematically on what we call the periodic table. I have one of these hanging in my classroom. I know you've been seeing them probably all the way back to elementary school. For this particular assignment, a periodic table will be helpful, as you'll see in a little bit. So I hope you can access one of those on the internet. If you Google periodic table, you'll get literally thousands of different variations. All right, and now we're going to jump into the things that make up elements, which we call subatomic particles. All atoms are made of subatomic particles. So when I said atoms are indivisible, that's not really true. We can't break them down into simpler things, but they are made up of smaller components. The prefix sub means below, and here atomic is referring to the scale of atoms. So this is below the scale of atoms. So those three subatomic particles that make up atoms are protons, which have a mass of 1 atomic mass unit, or Dalton, that is a unit of mass. You can look it up, and a charge of +1. So with protons, think protons positive. They are fixed in place in the nucleus of the atom. The second subatomic particle is neutrons. Neutrons also have a mass of 1 atomic mass unit, but they have no charge. So instead of thinking neutrons negative, please don't do that. Think neutrons are neutral. They're neither positive nor negative. They have no charge. And they are also fixed in place in the nucleus of the atom. And then the last subatomic particle, the most fascinating in my opinion, are the electrons, which have a mass of 0 atomic mass units for the sake of this particular lesson. Actually, their mass is small, but it is measurable. It's about 1/2000th of the mass of a proton. For right now, we'll just say electrons have a mass of 0, and they have a charge of -1. So electrons are the negative subatomic particle. Due to their small size, remember, small mass, almost insignificant, and their location on the atom, which is outside the nucleus, electrons are highly mobile and can be lost or gained by an atom. And in fact, any chemical compound that forms through chemical bonding in any chemical reaction is a result of electrons being lost or gained. So hopefully we have an understanding of those three subatomic particles: electrons, protons, and neutrons. I believe in the assignment there is a table where I ask you to try to organize all the information I just put out there in that last slide. Now we're going to talk about properties of atoms. The first main property of an atom we call the atomic number. The atomic number of an atom is equal to its number of protons, and it defines which element that atom is. So for example, here we see an atom that's made up of 3 protons, 3 neutrons, 3 electrons. Because it has 3 protons, I would say its atomic number is 3. And if I go and look on a periodic table and find the element that has an atomic number of 3, I will see that it's lithium. And so I would say that this is a lithium atom. If it had 2 protons or 4 protons, then it wouldn't be lithium anymore. And that is true even if you remove or add neutrons or electrons. As long as it's got 3 protons, it's still lithium. Similarly, here is another atom with 6 protons. And I know from looking at the periodic table that 6 protons means it's an atomic number of 6, means that is definitely carbon. And then down here, just to show you that atoms can get really large. So I believe that this is an image of a model of a uranium atom. So that has 92 protons because its atomic number is 92. The second important property of atoms is the mass. The atomic mass, or the weight of an atom, is equal to the protons plus the neutrons in the atom. Remember, those are the 2 particles that have a mass. Each one has a mass of 1. And so when we add them together, we can find the total mass of the atom. And that works because we're not counting that very, very small, insignificant mass of electrons. And so here in this particular example with lithium, it's got 3 protons, it's got 3 neutrons. So I would say its atomic mass is 6 AMU, 6 atomic mass units. This carbon atom, it's got 6 protons, 6 neutrons, so I would say its atomic mass is 12. And then lastly, another very important property of atoms is their charge. The charge, or how positive or negative an atom is equal to the protons minus the electrons in an atom. So this can be a little confusing because charge can be both positive or negative depending on what you have more of. Protons, the things that cause positive charges, or electrons, the things that cause negative charges. So I like to think about charge as kind of like a sporting event. In this example up here with lithium, I have 3 protons and I have 3 electrons on the outside. So I have 3 positives, I have 3 negatives. The game is tied. Those 2 cancel each other out and the net charge would be 0. If I were to remove this electron up here, I would still have my 3 positives, but now I only have 2 negatives. And so I would say that positive is winning and it's winning by 1. So that overall atom would have a +1 charge. Conversely, if I added an electron, or let's say for the sake of this example, I add 2 electrons to this lithium atom, well, I'd still have the 3 positives, the 3 protons, but now I've got 5 electrons. And so the electrons are winning, and they're winning by 2. So I'd say it's got a -2 charge. That's one way to think about charge. I'm going to show you another in just a second. And here we are. I'm going to give you some equations that relate properties to subatomic particles. If you're one who likes to think algebraically, these could be really helpful for you. So first of all, I'm going to define some given variables. I'm going to let AN equal the atomic number, let AM equal the atomic mass, and I'll let C equal the charge. Those are our atomic properties. And then I'm going to let P equal the number of protons, N equal the number of neutrons, and E equal the number of electrons. So hopefully these variables make sense to you. Now I'm going to link them algebraically into what are not too complicated of equations and can be really helpful in thinking about how subatomic particles determine atomic properties. So the first one's very straightforward. It's just AN equals P. The atomic number equals the number of protons. The second one is about the atomic mass. As we said, the atomic mass equals the protons plus the neutrons. So here we've got AM equals P plus N. And I'll stress at this point that you can use these equations like you do in algebra class. If I know two things and I don't know the other, I can plug in what I know and rearrange algebraically to solve for that thing I don't know. So here, let's say, for example, I have a lithium atom with 3 protons that's got an atomic mass of 7. 7 equals 3 plus N. If I solve for N there, I would subtract off the 3. 7 minus 3 is 4, and so 4 equals N. In other words, I must have 4 neutrons with those 3 protons to give me a total atomic mass of 7. And then the last equation, charge equals protons minus electrons. And hopefully here you can see that because of that minus sign, charge can be positive or negative. And a couple ways I'd think about this is if protons are equal to the number of electrons, any number subtracted from itself is going to get you to 0. If protons, the number first in the subtraction problem, is bigger than the number of electrons, then the charge will be positive because I have more positives winning the game. And conversely, if electrons, the second part of the subtraction problem, is larger than the number of protons, then the charge will be negative. So hopefully these equations make sense. I'm going to do some examples that are a leftover of when I reviewed this with IS Extend at the beginning of the dismissal. And so hopefully seeing me apply these equations will help solidify it even more. And then lastly, chemists tend to be either lazy or smart, but they take a lot of shortcuts. They use a lot of symbolism. And so we're going to introduce one bit of symbolism that they use. Each element has a symbol, which can be found on the periodic table. And the first letter of the symbol is always capitalized. The second letter, if there is one, is always lowercase. So when you look at your periodic table, you'll see that not all elements have a 2-letter symbol. Some have just one, like carbon is just C, oxygen's just O, hydrogen's just H. But others do have 2 letters, and if they do, that second letter will always be lowercase. So like here in magnesium, the M is capital and the G is lowercase. That lets me know that I'm talking about a single element and not potentially talking about a compound of M bonded to G. And then when writing out the properties of an atom around the symbol, we have a systematic way of where we place things. It always goes like this. The atomic mass goes in the top left. So you can see I write my symbol, and then up and to the left, I can write the atomic mass. The atomic number goes in the bottom left. It is given by the symbol. If you have a periodic table, if you know the symbol, the element, then you also know the atomic number. So sometimes this is left out, but for the sake of this, let's include it. That atomic number will always be in the bottom left of the symbol. And then lastly, the charge, if it's not 0, goes in the top right. So here with this helium atom, you can see that the charge is up and to the right. And you will add on either a positive or a negative symbol to indicate if it's positive or negative. But I will say if the charge is 0, then often that is left out. So if you don't see a charge, assume the charge is 0. I hope that all makes sense. I am going to do a couple examples of kind of how I want you to apply this in the assignment. And like I said earlier, these examples are from a review I did with IS Extend, and so I might talk like, oh, remember when we did this last semester? Just kind of disregard that. You have not done this yet. I was just recycling a video from them. Anyways, I hope you're doing great, and I look forward to seeing you on Monday morning. Please don't hesitate to reach out if you have any questions, comments, or concerns. Be well, everybody.
Alright, we're going to go through a couple examples from that recent problem set about properties of atoms and subatomic particles. Just as a reminder, we have done this before last semester when we were studying nucleosynthesis in the sun. I gave you 3 rows that I said we would do as a group. And very important, notice I do have a digital periodic table pulled up. If you just Google periodic table, you will find more than you know what to do with. So make sure you have a periodic table for this. That is our go-to tool here. With this first one, I've got carbon with a 14 in the top left and a 6 in the bottom left. The 14 I know is the atomic mass, so I can plug that in. The 6 is the atomic number. I know that atomic number is always equal to number of protons. That's one equation that we can use here. AN equals P. I know that the atomic mass is equal to protons plus neutrons. So if I have an atomic mass of 14 and 6 are from protons, then that leaves 8 for neutrons. And then notice how there's nothing written in the top right here. That would be because the charge is 0. And so I can plug in 0 for the charge, neutral atom. And if the charge is 0 and I have 6 positives, then that means I must also have 6 negatives. So I have 6 electrons. And another way of thinking that is charge equals protons minus electrons. So I'm asking myself, 6 minus what number equals 0? That number would be 6. So there's one example all completed out. Let's do another one. Here I've got a charge of +1, 60 neutrons, and an atomic number of 47. Again, I know the atomic number is equal to the number of protons, so I can plug in 47 there. Atomic mass equals protons plus neutrons, so 47 plus 60 is going to be 107. And if I've got one more positive than I do negative, and I've got 47 positives, then I must have 46 negatives, 46 electrons, or, going to this equation, 47 minus what number equals +1. Remember that charges can be negative. So putting it all together into the symbol over here, I check my periodic table. I notice that an atomic number of 47 is silver, Ag. I put that atomic mass in the top left, put the atomic number in the bottom left, and the charge in the top right. Just a reminder on Google Docs, if you want to superscript or subscript numbers, then the hotkey is Control period or Control comma. And here, this last example, I know all of the subatomic particles, and I want to find the properties of the atom. So if I have 15 protons, that is my atomic number. Protons plus neutrons tells me atomic mass. 15 plus 16 is 31. And charge is protons minus electrons. I have an equal number of positives as I do negatives, so no one's a winner here. It comes out neutral. And then putting it all together into a symbol, I check my periodic table. Phosphorus has an atomic number of 15. All right, phosphorus. I add the 31, the atomic mass in the top left, the 15 in the bottom left, and I don't need to write anything in the top right because the charge is 0. And those are some examples done out. You have more to do in the table. Please shoot me any questions you might have. Thanks, guys.